So the final is tomorrow, exam 5. It's cumulative, and there's going to be a question on rotating coordinate systems. And then lecture quiz 5 is cumulative. Same, yeah, 5. Yep.
And is that on the whole?
Yes, that's everything. Yep. Everything. The specific lyrics in the second verse.
What time is break?
Yeah, exactly. All of that.
It's for intermission.
Okay. Wow. Yeah, what I play today, that's going to be on there. Yeah, any questions about anything else on the test or quiz? And then problem sets. To turn in hard copies, you have to turn those in by the time of the test. I guess by the end of the test, but that's playing a dangerous game. And then if you want to scan them and submit them, there's a Dropbox now on D2L. And you just have to get those in by the end of the day, Friday. So 8 midnight. Okay. Any questions about the problem sets? Yep.
Oh, I was just gonna ask, is it final at the same time as class?
Yes. And so it's scheduled for 2 hours. I'm going to make it the same length as the other ones. I'm planning to stay until 4 instead of 3. So if you want to work on it for another hour, that's fine. I mean, I think I expect people to start leaving after 45 minutes or something, but some people like to go a lot, more deliberately. Okay. All right.
Is there a key to the first exam?
Yeah, I have a key.
Okay.
So yeah, just stop by 1324 and you can borrow it and I can walk you through those problems if you want. But for the final, to get ready for the exam 3 type material, just use those new practice problems. Let's just for this summer session, just forget that first set of rigid body practice problems, okay? All right, so today I want to start with, so if you have any questions about practice problems, I can answer those. When we're done with that, I have one more example on rotating coordinate systems. It's not really any different than the other ones, but it's just more practice with other people around and stuff. And I think, I don't know, to me, this is complicated stuff and it's tricky for everyone. And I think often your first reaction, at least I remember feeling this way, is like to go take your book and sit with it and try to yeah, you don't have a book, but to sit with it, try to figure it out. It's like, I got to figure this out. When really the best thing to do is just keep hammering through problems, and eventually it makes sense. And once it makes sense, the mechanics of doing it makes sense, then your intuition sort of catches up with that. Like, so instead of trying to make sense out of it, do a bunch of problems and you'll make sense out of it that way. Okay, and then the last thing I'm going to do is talk about the work energy principle. That's an energy approach for, you can use it for linkages. The work energy principle is the basic idea that conservation of energy comes from. I think in physics, at least I teach college physics classes, so maybe it's a little different in the calc-based physics classes, but we tend to deal more with conservation of energy. But conservation of energy is a special case of the work energy principle, so we're going to go back to the more general thing, and it's such a nice, simple energy relationship, and it works well for doing linkage calculations. Okay. So first, anybody have any practice problem questions or types of problems you'd like to see to get ready for the final?
Can you go over that?
Oh, yeah. Yeah, for polar. Yeah. Okay, so polar coordinates. So yeah, we didn't. Okay. Yeah, okay. So in polar coordinates, if you're tracking the motion of a particle, so there's your particle. It's represented by a distance r and an angle theta, right? And so the polar coordinates, like if you think about giving the polar coordinates that define a point, you tend to think of those as r theta. But, and this is sort of one of the more confusing things about this, the position vector is not equal to r in the r-axis direction and theta in the theta-axis direction. Okay, so those are polar coordinates, but those aren't the
You're saying like you have like an IJK.
yes, exactly. Yep. So right. So here's our coordinate system in polar. This axis is the r-axis, just like the x-axis or whatever in any Cartesian system. And this is the e theta axis. And so obviously, if these are the coordinates, you would write the position vector as r theta, except for the one minor problem that's not at all how you write it. So that's confusing. Instead, the position vector is just equal to r0, or r times the r-axis, okay, the ER axis. And it makes sense if you think about it. If you think about what vector components mean, it says how far do you go in one axis direction plus how far do you go in the other axis direction. You just go along the ER axis all the way to the point, and then you're there. You don't need anything else. Okay. Yep.
The axis orientation change
Yes.
with respect to theta. So how do you represent that?
Yeah. Okay. So it's a rotating coordinate system. So the coordinate system axes rotate to keep ER pointing at the particle. And the angular position of the ER axis is given by theta, right? Well, remember, omega is just theta dot. So that means that our omega vector, well, and it's not this. So I'm erasing the small omega because what we're talking about here isn't a rigid body rotating. It's a coordinate system rotating. So it's the big omega that we care about, that's relevant here. So big omega then is just equal to 0, 0, theta dot. Okay, that's just because of the relationship between angular position and angular velocity.
We don't really have a name for that z-axis in the coordinate system.
Yeah, we don't have a name for it, right? It's just the out of the plane, and it has to satisfy it has to be out towards us because the cross product of the first axis with the second axis has to be the third axis. Okay, and so if this is capital omega, then what is capital omega dot? Because that's going to come up in our, well, take the time derivative of this, and you get 0, 0, theta double dot. So now this all gets a little confusing because we have a rotating coordinate system, and everything about rotating coordinate systems, the whole reason we talk about it is because time derivatives get so complicated in a rotating coordinate system. So why did I just gloss over all of that and just take the time derivative here? What makes me think I'm so special I can just do that? So there's one thing about the way this coordinate system is rotating that, well, so when this coordinate system, so say it starts here, okay? So say it started at the green and then rotated to the red. At the green, what's the direction of the z-axis, the third axis? Out of the page. At the red, after all this rotation, what's the orientation of the third axis? The same. And so even though the coordinate system is rotating, the third axis never moves. And so you could think of this as, so yeah, so the one that it's rotating around never moves. So if you think of this as theta dot, I'll call it EZ. Okay, time derivative of that is theta double dot EZ plus theta dot EZ dot. For the R and theta axes, that's something that you have to worry about. For this one, you don't have to worry about it because it's not moving. Yeah. So this axis doesn't change in time. All right, so what else do we need? So we need the okay, so our position vector is r0, 0. And so finding the velocity and acceleration that are observed for, by someone rotating with this coordinate system is easy. You're just taking the time derivatives. So anytime you're given your position vector as a function of time, figuring out the components dot and the components double dot is just taking those derivatives. So this is just equal to r dot and components double dot is just r double dot 0, 0. And now we have everything we do to use those formulas. So we know that the velocity vector is equal to components dot plus omega cross p. So that's r dot plus 0, 0 theta dot crossed with position. What? Is that right? Okay, so then you get, so r dot and r theta dot 0, or the way you see it written more often is r dot er plus r theta dot e theta. And the acceleration is equal to the components double dot plus omega dot cross p plus 2 omega cross components dot plus omega cross quantity omega cross p. And so you get r double dot 0, 0 plus omega dot was 0, 0 theta double dot crossed with the p vector r 0, 0 plus 2 times 0, 0 theta dot cross components dot r dot 0, 0, and then plus 0, 0 theta dot cross 0, 0 theta dot cross r 0, 0. Okay, so that's how you derive those two formulas, which probably wasn't what you were asking, but okay, helps to see it again, I guess. And then, and I don't remember what the question was like in the practice problems.
When does the ER, E theta axis and the XY Cartesian axis?
Oh, yeah. Oh, yeah, going back and forth. That's right. That's right. Yeah, and then, so.
Were you just trying to show that when you're looking at it from a non-inertial, you don't get the correct acceleration vector?
Well, if you use, what's the function? Do you have those problems with you? I think it's.
There are like 6 parts to the question. Yeah, RP is sin P, P is sin phi.
Okay, so Yeah, so I think the thing is just in the past I've emphasized polar more than I did this time. Uh, so yeah, why don't you just not do those to get ready for the test, I guess. I mean, yeah,
Yeah, so focus on the public schools.
yeah, yeah.
That seems to be.
And the example problems, right. But I mean, so you can do it where, okay, so um, if you think of your x component, so to translate between, yeah, right, to translate between polar and just an inertial coordinate system, you can use these relationships.
In this case, it would be like theta t.
Whoops. That's right.
You could just put it.
So yeah, and then so with this relationship, and then r has to be equal to x squared plus y squared square root, and theta has to be the inverse tangent of y over x. So this lets you go back and forth between them. And yeah, so if you use this relationship, you can come up with all the same stuff, compare the answers, and you'll get the same thing. So the reason that I said, you know, do it in these, in this inertial coordinate system, calculate probably the velocity and or acceleration vector, and then figure out when the first time is that the r-axis lines up with the x-axis and the theta axis lines up with the y-axis. At that point, whatever time that is, those answers need to match, or else one of them doesn't work. And it's just another way of sort of checking, you know. So yeah, it does work. It should work. You should get the same thing. But the problem is, so at almost every time, there are different orientations. And so it's an easy conversion. You just use a rotation matrix, but it's not as easy as just looking at it at the instance where they match up, or else are off at 90-degree angles, and you can just switch component. Yeah. Yes, sorry, I erased the R, I think. Yeah, right. So I don't know. I mean, so yeah, I won't put a polar problem on the test, except on the quiz maybe, you know, like things about polar. But polar coordinates, that's something that comes up from time to time. So I mean, I guess at least remember it's in your notes, and you can go back and think about it next class when that comes up, you know. Any other practice problems or things anyone would like clarified? On which one? Is that the one? Oh yeah, so that's the polar one. Skip that one and just do 2 and 3. Okay. Yeah. It is going to be on the test, but just don't practice it. No. No, right, it's not going to be on the test. On the quiz, I might ask questions about some of the things I said about polar coordinates, but I won't make you do a polar question. The kind of questions you should expect are the like double rotation questions, you know, those compound, one rotation riding another rotation. Yes. Any other questions on practice problems? Okay. Yeah.
What's a good way of determining when we need to
Yeah. You need to use relative motion when the origin is moving. Well, not always. If it's moving, it might just be moving with a constant velocity, and then you don't care because you're worried about acceleration, and constant velocity doesn't have acceleration. But yeah, basically, so I mean, I think that's basically the way to think about it. Like, is the origin moving or are the axes? So is the coordinate system, like, if the coordinate system's just doing this, then you don't need it. If it's doing this or this, then you do need it, you know? Yeah, that's in 3D, it can be doing that too.
I think problem 2 or
In the problem set 3, when you use both the answers are supposed to equal each other.
Yeah.
Now, when you move the origin to the little plate,
Yeah.
disk or whatever, you use R for the little disk, just like when the origin is on a disk. But then when you use when you find out R for the big disk, you don't go backwards from the origin. You're still going to make it work. You have to go from the center of mass of the big disk to the origin instead of from the origin to the center of mass of the big disk.
Right.
So what's up with that?
Well, the R vector always goes from the center of a rotation to the point that you care about. So when you're doing the relative motion, you're saying the acceleration, what you're trying to find always is the acceleration of some point relative to the ground. Okay? So the relative motion equations say to do this, you find the acceleration of p with respect to the origin. That's the one that's most comfortable to do. And then you add that to the acceleration of the origin with respect to the ground. This one, your r vector goes to the origin from the center of rotation. Because you're trying to, because to do this one, your point of interest is actually the origin. That's just the way this relative motion equation works. You find, so we're trying to break up the acceleration of this point P into 2 steps.
you have to connect it to the ground, since the first arm that had that rotating disc wasn't directly connected to the ground.
Right.
The next arm was, so then you use that arm to
Right.
project it out on
Right.
the next arm.
But the subscripts of this, of the relative motion equations tell you, you know, in this one, the desired point is P. In this one, the desired point is the origin. And the subscripts tell you that. And that's why it's useful to remember that little, you know, be able to remember how the subscripts have to work.
And we need to use that because we can't figure out how much information.
Okay. Any other questions? All right. You've never sneezed before? Oh, really? That's funny. Yeah. What just happened? That was crazy. Um, okay, so all right. So this arm here is rotating this way at 10 radians per second, constant angular velocity. And this one is rotating this way with a constant angular velocity of 20 radians per second. This mass is 5 kilograms. And let's call the center of this rotation A and the center of this rotation B. And I'll call this member 1 and this member 2. Okay, let's say this arm is 2 meters long, and this one is 1 meter long. We're going to use a coordinate system oriented with X this way, Y. Well, not necessarily, but we already know what their motion is, so we don't care about them. If we act, you know, and we're not asked about it. I mean, so there's two ways those could come into it. We could either be asked to figure out what couples had to be applied to make that happen, then we'd have to deal with them. Or we could be asked what forces were required to make, well, no, that's the same one I just said. Or we could be given a set of loads and ask what the motion is. But instead, we're just saying, whatever it takes, these motions are created, and we want to figure out the motion, you know, what's going on with the mass here. And the z-axis has to come out of the page. And we want to calculate, so what's the force vector applied to the mass by bar 2. And we're first going to do it, well, okay, before I say that, so in this kind of problem, like if sometimes it's sort of different when a problem's written than if you know, like say that you're working somewhere and your boss says figure out the force that this is applying because we've had some of these bars bend and we need to know what kind of forces we're dealing with or something, you know. So in that case, I mean, you have to, there's no coordinate system given. There's no like, try it with the coordinate system fixed on this and then try it with the coordinate system on this. So if you were trying to, if you just encountered this setup, your first thought should be, do I have one motion riding on top of another motion? Okay. And yeah, in this case you do. So which one's the horse and which one's the cowboy? Yep, so this one is the horse. In other words, the one way to think about it, maybe the way to think about it, I guess, is the axis of rotation of the rotation of member 2 depends on the rotation of member 1, right? As member 1 rotates around, the axis of rotation for member 2 changes. That's not true the other way around, okay? no matter how this is spinning, the axis of rotation for one is just, you know, the y-axis. So now that we've figured out what's riding what, we can think about our options for where to put the coordinate system. We know that we want the coordinate system to rotate with member one, okay? That's just always the way it is. You want the coordinate system fixed to the horse. But we have two options. Well, more than two, infinitely many, I guess, but I always break it up into two options. One is put the origin at a place where it's fixed to the ground, okay? That way, the only thing you have to deal with is the rotation of the coordinate axes. And the second way is put the origin somewhere where not only are the axes changing orientation, but the origin is accelerating too, okay? So what are the two spots where I'm going to say, so part A and part B, what are the two locations of the origin I'm going to choose? Yeah, the two that, and those are also the only 2 points I named, so that makes sense. So do it first with the origin at A, and second with the origin at B. Okay. What? Do it first. I think most people would, so the simpler way is probably the way at A. It's kind of unnecessarily complicated to put the origin at B unless that just happens to be the only place that you can take good measurements, which is possible, I guess. You know, so I would guess that usually I do it with the fixed origin first and then do it with the accelerating origin, but yeah, notice that that's the difference that we're talking about. In both cases, the coordinate axes are rotating, but with the origin at A, the origin is fixed to the ground. With the origin at B, the origin is accelerating. And so you have to deal with that too. So, okay, work together on this. I guess let's just do part A first. And what? So how about at 5 after 2, I'll go through this. So you can take a break, work on this. 5 after 2, I'll go through part A, and then you can look at part B. 2 meters. 2 meters and 1 meter.